Oh, it's a beautiful equation, all right. It's Mandelbrot's equation. It's Mandelbrot's recursive equation. There it is, right here. What does it do? Well, it takes a complex number, some point on the complex plane, and it tells you what color to color that point. That's it. If you input a number, you select a number on the complex plane, call it point C, and input it to Mandelbrot's recursive equation, it will come out with a designation as to what color to make point C on your graph. And that's it. Now what that says is that if you're going to make a big graph and you're going to make some fancy fractal, that means you got to input a lot of points, of course. But that's your choice. How many you input, where they are input, and how close they are together is the choice of the user. What the recursive equation does, it simply tells you the color of each and every point that you input. It doesn't criticize, it doesn't decide on its own, it doesn't say, hey, you're not giving me enough, or they should be closer together or farther apart. It simply gives you a color. You do your own picking, and it'll tell you what color each of those points are. And that's its job. And we're going to be looking closer in the next few slides as to how does it do that? How does it know? Let's learn a little bit more about Mandelbrot's famous equation. We'll go through the mechanics of this in the next slide, but for now let's just look at it from a top level, that this equation does produce a Mandelbrot baby. And it does so by providing points going into the equation. And as these points go into the equation loops, goes around and around and around, but it halts when one of those points jump out of the circle of radius 2. And each time it loops, n is incremented. So n will always have the value of the number of loops. So when it stops, then we know that n is the number of loops that it completed. And then we can tell what kind of point it is. For example, if you select a point out here outside the baby, and we're trying to draw this graphic here, this would be a white point, background. And what would happen is if you selected it and ran this equation, it would come back and it would say it would be greater than 0, but less than 41. So anything from 1 to 40 would be background. It would tell you that this is a white point you just picked. It's a background point. And you didn't know that. You just picked the point. It told you that n, let's say n was 20. Well, you go, okay, 20 is between 0 and 41, so it is background, it's white. Well, let's say you pick a point on a fractal that lives on the surface of the baby. You pick a fractal, and you pick one of those points, you feed it to the equation. Well, n comes back. If it's greater than 40 and less than 1,000, it's a fractal. So what will happen, of course, is, you can color a fractal anything you want to color it, really. But you might have certain colors prescribed. One color for 41, one color for 42, and one color for 43. You could have all of your color patterns all the way up to 1,000. You'd have beautiful fractals. But now, let's say you picked a point here, a black, inside the baby. It would come back, it would be greater than 999. It would be greater than 999, and it could go on to infinity unless we stopped it. Because set members continue to loop forever. If you're a black pixel, it'll loop forever. So we have to have some kind of upper limit that says if you go to 1,000, you can stop because we know you're black. And that's what happens. We put a little trigger mechanism here that says you can pass the border test all day long, but if you pass over 1,000 of them, you're going to be black. We'll call you a set member. So that's how it works. Let's just review it real quickly. To produce a Mandelbrot baby, you pick points from the complex number plane, and you feed them to the equation, and it loops. It continues to loop as long as it doesn't jump outside the circle, but eventually it will jump outside the circle. And when it does, that's the circle radius 2, and when it does, we can record the value of n, how many loops that occurred. And knowing n, then we know whether it is a background point, whether it is a fractal, or whether it's a set member. We know whether it's white or black or something else, some choice that we might want to make with regard to fractals. We could make them all green if we wanted to. We could have black, we could have white background, we could have black set members, and we could have green fractals, so that's what we wanted. But we would know that because of n. Okay, let's look a little closer at this equation. And let's look at it as if it were an engine we could start up, because it really is an engine when it cycles like this. How do you start the engine? Well, the first thing you have to do is initialize the engine. If this was an engine, you would put gas in it. You would put some oil in it. You would get it ready to run. And how to do that on equations is you set your n to 0, because n is very important. N counts the loops. So we want to make sure we start off at 0. And since this computes in Z0, Z1, Z2, Z3, Z4 as it goes around and around, we want to make sure it starts off clean. So we assign Z0 equal to 0 as well. Okay, once that's initialized, then we're ready to start the engine. To start the engine, we have to input a complex number, C. It can be anything, as long as it's on the complex plane. And once that happens, then we know what C is with regard to this formula. We know what C is because we just input it. But what is this? What is this here? Well, and what is this? Well, we've taken this equation, we've written it over here. So this is the same as this equation right here. Well, we know that n is 0. We know that. So let's put a 0 every place there's an n. So we'll put a 0 here, and we'll put a 0 here. So now we know that z to the 0 plus 1 is equal to z sub 0. Let me restate this again. Z sub 0 plus 1 is equal to z sub 0 raised to the second power plus c. When we add 0 to 1, that becomes z1. So now we can say that z1 is equal to z0 squared plus c. What is z0? Well, z0 is 0. So we know that z1 is equal to 0 squared plus c. So that means that z1 is equal to c. So we know what z0 is, and now we know what z1 is. Well, this is the first time through Z1 is calculated, and it's sent to the loop. Z1 is sent down here, and the border test is made. It asks the question, is this point C outside the circle, yes or no? Because if it's outside the circle, it doesn't want to do anything. It doesn't want to have any more to do with it. It'll stop the engine. So it asks that question. And in the process of asking that question, it increments n. Whatever n was before, now n is 1 greater. So first time through, n was 0. So n is equal to 0 plus 1. So now n is 1 because it's looped. It comes back up here, and it's ready to determine what Z2 is. We know what Z1 was. So what is Z2? Let's talk about that. Okay, so here we have n now is equal to 1 because we've looped 1. And now Z sub 1 plus 1, because n is 1, is equal to Z1, because n is 1, plus C. So we add 1 plus 1, we have Z2. Z sub 2 is equal to C. Where'd we get that? Right from here. We knew Z1 was C. So Z1 is C, C squared plus C. So we now know that Z2 is equal to C squared plus C. So C squared plus C, or Z2, goes around the loop. The border test says, is the point that this equates to, whatever point that is that outside the circle? Because if it is, it'll stop. Otherwise, it'll press on. It will increment n becomes 2, and it'll come back here. Now, we could continue to do this, although I'm not sure that you would really want me to do this. But we could go through Z3, Z4, Z5, all the way up to Z1000 if we wanted to. But the message here is that the equation takes a point, squares it, and adds another point to it. This is one point here, because each of these resolve down to a single point. It takes a point and it squares it and adds C to it. Takes a point, squares it, and adds C to it, and so on and so forth, no matter how complicated this looks. By the way, as if you'll notice, n is equal to 7. There's 7 C squareds here. Squared, 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 7 of them. But no matter how complicated this looks, this is nothing more than a point squared plus another point. And so what we're going to do is we're going to generalize that and say if we had an equation that would square a point and would add another point to it, that's basically what that does. Here's an example. This point A1 plus B1i, and we square it. We add A1 plus B1i, that's another point, to it, and it comes out to some Z2, which is some real number here and some imaginary component over here, N1i. All of this reduces down to 1 point again. So that's the good news about all this complicated stuff, that it always reduces down to another point. And that other point can be evaluated with regard to the circle of radius 2. So what we're going to do is we're going to look at this rather complicated equation. You can see this is fairly complicated. We're just going to reduce it down to this, and that is we're going to be able to take a point and square it. We're going to add another point to it. If we can do that, we can do this. Sound fair? Well, here we go. We're going to be doing some binomial multiplication. Binomial meaning it's got two terms. Now, if these weren't complex numbers, then we could just simply do a FOIL and we'd be done with it. And we'll talk about what a FOIL is in case you can't remember from algebra. But if it wasn't complex, it would be a little bit easier. But the complexity of this makes it just minor little change we have to make here, and we'll talk about it. So these are two complex numbers. We're going to multiply them together, and we're going to add another complex number to it, which is basically the pattern that we have been talking about. What is this FOIL thing? Well, it's a memory trigger that stands for first, outside, inside, and last. And what does that mean? Well, this means that the first thing you do is to multiply the first terms together. Multiply A1, that's the first term here, and that's the first term over here. A1 times A1. So that's A1 squared, A1 times A1. What's the next thing we do? We multiply outside terms. Well, the outside terms is A1 times B1I. And then the inside term is A1 times B1I. So we're left with 2 A1 B1I. We got one from the outside terms and one from the inside terms. 2 times A1 B1I. And the last thing we do is multiply the last terms together, which is B1I times B1I. Well, this is where the twist comes in, because we're certainly left with, when we square B1, we have B1 squared, obviously, but we have an element in here that's a result of a complex number, because when you multiply I times I, the result is -1. So the nice little B1 squared that we had there turns out to be minus B1 squared. You can see that down here. The answer now is A1 squared minus B1 squared plus 2A1 B1I plus A2. Where'd that come from? Okay, that's here. We're adding the other point into it, plus A2 plus B2. And if we add all of these up together, we would come out with another complex number. And that would be how that we would multiply two points together and add another point to it. All right, let's look at an example. The example I've chosen is, the point is 0.3 plus -0.5i squared. So we'd multiply this times this. And the other point will just make up a point, 0.16 plus a positive 0.34i. So here we go. We're going to apply this technique to two actual complex numbers plus another one. So the first thing we do is multiply the first terms together. 0.3 times 0.3. Well, that's A1 squared, or A1 times A1, which is 0.3 times 0.3, and that equates to 0.09. And the next thing we do is we multiply the outside terms together. Well, that's 0.3 times a -0.5i. 0.3 times a -0.5i. And if you'll notice, the other term, the inside term, is the same. So what do we have here? We have 2 times A1 times B1I, which is the same as saying 2 times 0.3 times -0.5i. So this would be one of the products, and then there's another product because we did it both outside and inside. We multiply these two terms together and multiply it times 2. The answer is -0.30i. Lastly, we multiply the last terms together, which is -0.5i times -0.5i. And that's the same as b squared, or b1 times b1. Let's not forget the -1 that comes into play with I times I is -1. And when you do all of that, you come out with a 0.25. And don't forget about C, because we have 0.16 we need to add into that, and we have a positive 0.34i to add into that. We put it all together, we have 0.09 minus 0.25 plus a negative 0.30i plus 0.16 plus 0.34i, and this all, we join the reals, which is this one, and this one. It comes out to 0. You can see that 16 and 9 is 25 minus 25 is 0. And then we join this one with this one. Now 34 minus 30 is 4. So we have 4i. So the new point, after doing all of this stuff, the new point is 0 plus 0.04i. And that's an example of how we are going to be able to implement Mandelbrot's famous equation. Okay, we're going to look at a simple little Visual Basic program to do this. To square a point and add another point to it. And we're also going to test it to see if it passes the border test. So here we go. This is it. This is not a very complicated thing, and we're going to take it real easy, take it one step at a time. The first thing I want you to notice is that there is a loop here that goes from 4 to the next, and it goes up to 1,000. And what it does, it keeps looping until it looks for a border test violation, which is what that is. If it finds no border test violation for 1,000, it drops down to here and it says it's a set member. All right, so let's back up. Here we go. First thing we do is we are given an A1 and a B1 and an A2 and a B2. First thing it does is it does some initialization, and it does the arithmetic. It squares A1, it squares B1, multiplies it times -1, just like what we did. It takes A1 and B1 times 2 to account for the other multiplications. So now square 1, square 2, and cross 1 are the results of all the mathematics that we did here. So now we need to make the new point. The new point is square 1 plus square 2 plus A2, and A2 is the other point, the C that was defined going into this equation. And we put all these together, we collect the real parts together, just like we did in the example. And we come up with a new B1 by adding cross 1 with B2, which B2 is from the other point. We have the imaginary part. So we've done two things in this one section. We have done the mathematics, which we had done in the example, and we came up with a new point, just like we did in the example. So now we have a new A1 and a B1. Well, what this is, and keep in mind that this terminology here is a little confusing, but A1 top hat 2 is the same as saying A1 squared. That's the same as saying A1 squared. That's obviously saying B1 squared. Well, it turns out in geometry that if you have a circle whose center is at the origin, then you can take any point away from that origin, and you have an A1, like for example on the x-axis, and B1 on the y-axis, and you square them and add them together, and that will give you the radius squared. The radius squared. So 4 is the radius squared. Well, what's the radius? Well, the radius is 2. All right, circle of radius 2. So what happens is we're asking this new point A1 that we came up with and the new point B1, we squared them and added them together. Is that sum greater than 4? Because if it is, it's outside the circle. Let me say it again. If it is, it's outside the circle. Well, if it's outside the circle, the engine stops, basically. We don't want to go through any more loops. We want to go down here. If it just jumped outside the circle, and so we're saying if I, and by the way, I is the same as the n that we were using before, so let's not get that confused. We're saying if n or I is greater than 40, then it's a fractal. We need to record those coordinates and do the row counter, whatever else we need to do, and we get out of there. Okay, we get out of there with j set to 1, by the way. The only way we can jump out of that loop is setting j to 1. When it comes down here, well, j is not 1. I mean, if j is 1, it doesn't do this. Well, we don't want it to do set members because we know it's a fractal. It's not a set member. So by setting j equal to 1, it will not do this, even though we jump out of the for loop. Boom. Now, if it's not greater than 40, then it's background. All right, so we collect the coordinates that define the point for the background, and we exit the for. Also, j is 1, so it won't do this. So the new point that we have is either a fractal or a background point. If it does not encounter any of the boundary value violations, it will flow down here and j will be 0, and it will record the set member. So this section performs the recursive calculations. This section is the border test, looks for border test violation, and it does that by squaring a1 and b1 and seeing if it's greater than radius squared, or 2 squared, or 4. And this last part identifies the Mandelbrot set members. So that wasn't too bad, was it? We fed a point into the Mandelbrot recursion. We found out whether it's a background member of the set or a fractal. And by the way, if you have not seen the naked Mandelbrot, which is the precursor video to this one, you need to see that. And that's on fractallog.com, fractallog.com. So just for a review, we found out the fractals are border violators, and they're greater than 40 and less than 1,000. We also found out that backgrounds are border violators as well, but they are less than 41. Okay, less than 41, greater than 0, and they're red or white in the case of the example that we were using. So that takes care of the fractals and the background points. The only thing that's left is the set members, and of course the only time it gets down to do this is if it had not violated the border, but went through all 1,000 loops and got down here, and then it proved it was a set member and it was colored appropriately. In the example we were using, it would have been colored black. So there you have it. Fairly simple equation. You can do this in many different languages and really accomplish the same thing, and you will have a Mandelbrot generator. It's a beautiful equation. Squares a point and adds another point to it, and checks to make sure that it's in the circle of radius 2. Very nice. What do we get? We get the whole Mandelbrot egg is what we get. Depending upon the color assignments, depending upon what we want out of this. We can make it from 2 to 2, or just do just the Mandelbrot. We can ignore all the blacks and reds and just do the Mandelbrot, because we're in charge of that equation. We're in charge of the color assignment as well. The Mandelbrot baby, working inside a circle, a radius 2. It's a beautiful equation. Again, if you haven't seen the naked Mandelbrot, check it out, fractallog.com. This video, as well as many other videos, are also on fractallog.com. Hope you've enjoyed this. My name is Dave Fashenpour, and thanks for coming along.